Thanks very much. So thanks for the invite. It's a pleasure to be here. It says Santa Barbara here, but actually, unfortunately, I'm located in Boston. So the weather is as bad as it is here, actually. So I decided to talk about evasive malware today because I think that's the next step, right? So we're doing a lot of malware analysis today. We do malware detection. But what's going to happen, right? And I'm actually willing to bet money on this. So I'll give you some examples of what's going to happen and why I think that these things are going to happen. So I am actually also a professor at Northeastern University, so I've been doing malware research for the last 10 years or so. And I'm one of the co-founders of Lastline because the idea was to take our research that we published, disseminated, we built systems that are being used by quite a number of people. I don't know if there are any Anubis users here, but this is a system that we built. So the idea was to take that research and to make something more useful out of it. That's one reason why we actually founded Lastline. So malware has been evolving, and automated malware analysis has become a huge issue today, right? Why is that the case? Because, I'll show you some graphs, but like 10 years ago, maybe we were receiving 1,000 new malware samples every day. Today, can anybody guess? I don't know if anybody is into malware analysis here.
Over 1 million.
Per day? Yeah. Per day. I would say more like 200, 300,000. But 1 million is very reasonable, right? Soon it's going to be 1 million new samples that we receive every day. So how can you analyze that? Right? It's actually a huge challenge to be able to do this. So we've been seeing trends, right? You're all familiar with this. So, we were seeing cyber vandalism. We saw a lot of cyber crime. And now, increasingly, we started talking about targeted attacks, right? So rather than launching general attacks, people are more into launching specific targeted attacks against organizations to compromise them and steal interesting information, right? So that's the next step. Interestingly, 5 years ago, we were talking about this. Nobody was taking it as seriously as they're taking it today because there's a lot of evidence today that it's actually happening, right? The guy on the street knows about this because they read it in the news, right? It's actually a very well-known thing now.
Engin, my wife knows about it.
She knows about that? Okay. Like, that's the ultimate proof. So there's like, exactly. My grandma has heard about this.
My wife should not work anything that plugs into a wall. But she's not here, so.
So how do we do malware analysis traditionally, right? So typically, people actually sit down. These are all the debuggers you start. If you have one sample you want to analyze every day, you sit down and you analyze it manually, right? It's actually very cool because you can find out a lot about that. You look at the running processes. You look at the network traffic, right? You look at the dumps to try to find out what is being actually sent outside. It's actually very interesting information, right? But to do this manually takes a lot of time, right? So that's why automated malware analysis started becoming very popular. That's why you're seeing a lot of companies now that are actually providing tools that allow you to analyze malware automatically. But the question is, this you can do pretty well. If you're a sophisticated malware analyst, you can sit down, you can extract a lot of interesting information. But if you do this automatically, sometimes you lose information, right? So how can you make this analysis very efficient, very, very effective? These are the research questions. So this is what I mentioned to you, right? Like back in 1984, there were basically viruses, but it was not a huge issue. But in the last 10 years or so, we're seeing an exponential growth in the numbers of malware samples we're seeing. It doesn't mean that these are all new malware families, but because the bad guys are using tricks such as obfuscation, encryption, the way the malware looks keeps changing, right? So after every infection, it's the same malware, but just looks different. That's why when you first see it, you don't have the source code and you're not able to say if it's the malware sample or not, right? Manual analysis takes a lot of time. Looking at it statically without running it, it's actually a huge problem. So scientifically, there's a lot of proof that where people have shown that it's not feasible. That's why the idea was, why don't we take these samples and run them and look at what they do, right? So that's why the Sandbox became very popular, right? It's not a super new technology. It has been around. Even in 2005, people were actually using sandboxes. But now, these are going into products, right? These are becoming parts of products. And people, security specialists and experts are expecting this. If you have a good network solution, you need to have a sandbox, right? So automation is great. So looking at things by hand, it doesn't scale, as we discussed. So why don't you just build an instrumented environment, an environment where you can actually put the malware, say put it in a prison, run it in the prison, and look at what it does, right? Does it connect to the outside? Does it try to exploit you? And look at this thing dynamically just by executing it. That's the idea that many people are actually investing in now, because this seems to be the only feasible thing you can do right now. So we started doing this as well back in 2003. We built a system called Anubis, analyzing unknown binaries, and the idea was take an executable and analyze it as well as possible, right? Try to extract some intelligence out of that executable, although you don't know anything about it, right? And the way we chose to do it at the time was it was based on an emulator rather than a virtual machine, and I will be talking about the difference between both, so that you're able to see every single instruction that the malware is executing, so that you can actually find out exactly what this thing is trying to do, right? Is it trying to look at your information? Is it sending it over the network? So being able to track every instruction is actually very useful because it allows you to see exactly what this thing is doing. Another thing, this is actually pretty scientific, we wanted an environment that allows us to do taint tracking. So taint tracking means that you're able to do data flow analysis, which means that you actually see what data, how data flows through that executable. So if I run it, I actually see what is being read, and I see how that read information is being, say, sent over the network, right? This is very useful for you if you want to build high-level models for detection. A classic example is if you execute something and you see that it opens its own code, it starts reading it, and then it sends it over the network. That's a classic sign for a worm, right? Because the worm, a virus, actually copies itself and then replicates, right? So you're interested in building high-level behaviors like that. And if you're not able to do dynamic data flow analysis, this becomes very tough. And right now, most of the sandboxes out there actually are not able to do this. So if there are Anubis users, they'll be familiar with this. So we have thousands of users. These are university services that we provide for free, basically. People submit samples to us. We analyze them. We generate nice reports for them. And interestingly, it was nice for us to see as researchers that these systems became very popular and they became part of workflows, right? So if you go to, say, DARPA, they're using this. If you go to many security companies, actually people submit samples to us because they like this advanced sandbox, right? So our idea was, let's take this, let's use this as a research platform, let's experiment with it, look at all the problems we see there, let's try to improve upon that and maybe build something that's better than what people are using out there. So I talked about evasion and emulation, right? So what's the difference? So typically, building a sandbox is actually not a big problem. When I teach a class, and I teach security classes, I actually tell students to build a sandbox, and it takes them maybe a day. I can take VirtualBox, I can take VMware, I can instrument it a bit, I can run a sample, and I have my sandbox, right? I can see more or less what this thing does. What's the problem there? The problem there is that if you're using a virtualization technology, say like VMware, VirtualBox, any popular technology, you actually see system calls, right? So you see some low-level information. You would see that, say, the file is being opened, you see something is being read, and then you would see something is being closed, right? But you don't have much information here. Everything in the dark is what the bad guys can use to evade you. And I'll show you examples of how this evasion actually happens in the wild. So this is the classic approach, right? So my advice would be somebody tells you, I have a sandbox, ask them, how do you deal with evasion? Because it's actually a huge problem. If you're using emulation and emulated hardware, and there's an open source tool out there called QEMU that many people use, it actually allows you to see every single instruction that is being executed. So if the malware does some tricks to evade your analysis, say, they look at certain file names, etc., you at least have a chance to catch that, right? So this would be, this is what you would see. You would see every instruction that is being executed. So at that time, we actually chose to ignore this because we thought this would be lame. And Anubis is actually built on this approach of emulating the hardware so that you're actually able to see the instructions that are being executed. So I mentioned data flow analysis, very scientific, so I'll just briefly talk about what it is. So the idea, as I was saying, is to allow you to build something on top of this emulator so that you also see how data flows through the malware, right? This is very interesting information for you because it allows you to build high-level models, basically. So you have taint sources, so-called taint sinks, and you see how sensitive information actually flows through the execution. It's very scientific. There are a lot of computer science papers where people have shown how this can be done. So this is also something that we're actually using to create these high-level models. So what is the problem here? So if you're the bad guy, start thinking about this, right? You write malware sample, you infect people, people find it, they run it, right? So obviously, you're smart, so you would do evasion, right? They're not stupid people. They're actually sophisticated people, especially in sophisticated attacks. They know by now that people use dynamic analyzers, they use sandboxes, they use VMware. So their aim, of course, is to create malware that tries to detect if it is being analyzed or not, right? This is actually something that would be useful for them. So because the code is executed, there are quite a number of things that they can actually do. So they would develop code that when you run the code, this malware sample, it would detect that it is being analyzed, and it basically changes its behavior, right? So it might, for example, do something completely different. It would do something benign rather than doing something malicious, right? Because you're the bad guy, you're smart. And there are different ways of doing this. So classic techniques are you detect the underlying runtime environment, right? You might try to detect if you're being run in a virtualized environment. Is VMware being used? Is VirtualBox being used, right? Is something popular being used? If so, and you can create checks in your code, you completely change the behavior, or typically, they stop doing anything. They basically just exit, right? So if you're analyzing a malware sample and you know it's malware and it just doesn't do anything in the sandbox, that's very suspicious. That's often a sign that this thing is just evading you. Also, malware can detect signs of specific analysis environments, right? So they might check certain operating system artifacts, certain file names, certain processes that are running. All sorts of things anything they can use to detect that specific analysis environment. So they could also do lame things, which are actually very effective. For example, just wait until someone clicks on something. You're running the code, and typically you're not interacting with the code, right? If you're just waiting for a click, it's very easy to bypass this analysis environment. So one example I'll tell you about Anubis is that, so the PhD student who was actually writing Anubis, his name was Andy, and we started seeing malware samples that were being submitted to us, where the malware was checking the username, right? And if the username was Andy, it was changing its behavior. So whose name is Andy here? So you're actually safer against malware. Just to show you that this is actually real, right? So the advantage of having a research thing like this outside and letting people use it is Anubis became a very popular analysis tool, and we started seeing malware packers, malware tools that actually had anti-Anubis checks in them. So if you look at this costs something like $20. The bad guy writes the code. If you just check this, you're not able to see it, right? So from a practical point of view, this sounds terrible because we don't detect it. But as researchers, this is great because it actually shows us a new problem, and then you can start thinking about how they actually deal with this problem. Another one, you would see that there's an anti-sandbox check here. You'll see Norman, Anubis, CW, generic sandboxes, blah, blah. There are a lot of things, right? So if something becomes popular, I would bet money on that at some point it's going to be evaded, right? So the question then becomes, how do you design something that is less, it's more difficult to evade? So that's the challenge, I think. Here, again, Anubis is here. So we have a lot of tools out there that actually actively try to evade us, right? We know it, and we deal with this. Another classic trick that used to be very popular was the so-called red pill test. So if you executed this piece of code in a virtualized environment, it told you automatically if the code was being run in a virtual machine or not. Very simple code, you run it, and you don't even have to be sophisticated. Anyone can take this, anyone can run this, and they know they're actually being analyzed, right? Today this changed a bit because of the hardware virtualization support, but this used to be very popular 5 years ago or so. So there's this constant arms race, and you need to be able to deal with these things. What else could you do? Well, you could look for CPU bugs if it's an emulated environment. So you look for unfaithful emulation, right? And people have actually written papers to automate this. There are research papers where people have shown that this is actually very easy to do, right? So today the malware cannot assume anymore that just because it's being run in a virtualized environment or just because it's being emulated, that it is being analyzed. So this assumption doesn't hold anymore, but there are many other things that they started doing, right? So it's a constant evolving problem, basically. What kind of tricks are possible? Anything you can imagine, right? The things you can do are only limited by your imagination. For example, you can check the Windows XP product ID. So when we were running this at the university, we had a specific product ID. After a while, they started learning it, and we started seeing malware samples that were checking for that product ID, right? Or checking for a specific username, like Andy, as I told you. Or checking for unexpected DLLs, certain mutex names, right? They analyze your system, because at some point they will get access to your system, and they will analyze it. So they'll find out ways of evading it. Or simpler things like checking the color of a background pixel, right? So if you have a nice desktop picture in your virtualized analyzer, they might tune their malware to that. Or they might check for the presence of 3-button mice, right? Or a certain keyboard layout, because the assumption is that if you're analyzing it, there's a good chance that a mouse is not attached to that virtual machine, right? So these are the type of tricks that they use, and they actively use these to actually do evasion in the wild. This just shows you that, when we manually disassemble some of these malware samples, we do actually see these, active checks in them. So something that you see quite a bit. And we've also seen quite a number of discussions in hacker forums, right? So here they're actually discussing how, somebody posts a piece of code and says, use this in your malware. If you do, then you'll be able to detect these sandboxes, right? And these are currently many of the public sandboxes out there. But if you're using a specific product, and if the attack is very sophisticated, you need to assume that, somebody will actually look into ways of evading it at some point. To avoid monitoring, you can do all sorts of things, like you can open a window and wait for the user to click. And typically, if you're doing this automatically, nobody clicks on it. So the way we deal with that is we run a malware sample and start clicking on things randomly or using certain algorithms. Or you could do bad things after the system reboots, right? You just wait for it to reboot and then you start doing bad things. Or this is a classic, and we've seen worm samples that actually do this. You run before or after specific dates. Suppose that it's a targeted attack and they want to launch it in 2015. There might be a date check there, right? So you run the code, it doesn't do anything, right? So how can you actually go after these triggers, and how can you find these triggers, right? These are all things that are not difficult to do. The fact that we're not seeing them as often in most of the publicized APTs doesn't mean that they're not going to happen. Right now they don't bother too much, but the next step would be they'll start doing these things. Again, it's just a piece of code that shows you how you can do a date check. The simplest thing you could do, and this is something that many sandboxes actually are not able to deal with, is that you basically sleep. What does that mean? You run the sample, and you can just have one command that just makes it wait. Typically, because you're dealing with a lot of samples, you have limited time to analyze it, and you might choose to and says this thing doesn't do anything. So very simple trick, but enough to evade many sandboxes out there. So one thing we've been seeing, and I'd like to show you that because it shows how complicated these things are becoming. So sleep is something that you might be able to deal with easily, right? So if somebody is waiting for 15 minutes in your sandbox, there are ways of finding that out. You detect it, and then you basically speed up your time, right? There are certain things you cannot do, and that's why the bad guys have started using so-called stalling loops. So what is that? So this is real code from a malware sample. So basically, it's a piece of code that doesn't do anything. So it's just, it's a loop. The problem is, if you run it on the real host, it takes you a couple of milliseconds. But if you run it in an analyzed environment, it actually takes you maybe 10 hours, right? Why is that the case? Because every time you're executing this loop, something is being logged somewhere. So you have to write something into a file. You have to do something with the memory. And they take advantage of that, right? So very simple, inexpensive thing to do, and sophisticated attacks are actually making use of stuff like that. So the question then is, what can you do about evasion, right? So I talked about all the problems. So many evasion techniques actually depend on checking for specific values, so-called triggers, right? So a good thing to do could be to look for these triggers, and then to look for to try to maybe randomize certain things. So if you're looking at the environment, right, after every execution, maybe the product ID should always be randomized, right? The background should always be randomized. Certain checks, hard disk names, etc., should be randomly generated at each instance so that they can't actually tune their code on these things. Or the ideal thing to do would be to detect most of these triggers automatically and to try to bypass them, right? If there's a date check, it would be great if I can detect the date check and maybe just find out what would happen if I reverse that check, right? So these are the type of things that we've actually worked on, and there are papers, if you're interested, where we actually say how we do these things that are quite promising, and some of these things have also been implemented. So One thing that we're able to do is bypassing triggers, right? So the idea is every time there's a certain check, say check for an environment variable or check for a certain date, what you can do is during the analysis, rather than execute the code only once, you go through the code. Because you're able to see every instruction, you can basically pause, create a snapshot, and explore alternative branches, right? If there's a date check, you stop there and you look at what would happen if the if statement is true. So you would take one branch, you would explore that branch, and then when you're done, you basically jump back and you explore the alternative false branch, right? And if you're able to do this automatically and efficiently, that allows you to see and bypass these triggers in the code, right? It's not something that is very trivial to do, and it's not something you can do if you're using a virtualization technology. This is only something that you have a potential to do if you use some sort of emulation technology, right? Conceptually, that's the only possibility you have. So again, data tracking becomes interesting and important here because you're able to track interesting input, and by tracking this interesting input, you're able to explore these, the different branches. What do you do against stalling loops? So what we're doing right now is that because we're seeing these instructions, right, we actually detect the loops, so we can actually see when the code starts stalling, and we have different modes of operation. So whenever we detect that the code is stalling, we basically just jump over this loop, right? So we actually make it much, much faster. We disable the logging and then start logging again once the loop is finished, right? And to do that, you need to identify loops. There are a lot of CS techniques, there are algorithms that actually allow you to identify loops in code, and these are the type of things that we actually make use of, right? And when we find them, we basically are able to deal with stalling loops. And in the sandbox we have right now, we don't call it sandbox, it's in the analysis environment basically, we are able to see these stalling loops, and Lindsay will be showing you some examples of that. So high resolution analysis, I think, is the way to go forward. So this is something that we invested quite a bit of effort in. So the idea is, you can do analysis, but how can you do evasion resistant analysis, right? So this is something that I think will be a very important issue pretty soon. So you need to identify evasive checks. Is your system going to be perfect? Unfortunately, it will not. There's no silver bullet, but you need to come with technologies that are extensible and that give you a chance to deal with some of these evasions, right? At least classes of evasions that you can deal with. So there are all sorts of tricks they can use, but you want to cover as many of them as possible. So you want to increase the difficulty bar for the attacker. You don't want to make it trivial for them. So information flow tracking, I think, is very useful because it allows you to see also in the reports how this information is being transferred, right? You might see that you see the dependencies between different system calls, right? You see something is being read and something is being copied over the network. Like, these are the important things, basically. Another important thing is, I think, correlation. So the problem you're facing today is that you can analyze things, you can generate all these reports, you can say something is bad, but often people generate a lot of alerts, right? And it's very difficult to know what is interesting for you and what is not interesting for you, right? So this is something that we also invested quite a bit of effort in, and we're just going to show you in the demo, but we won't go into technical details. Let me know if you're interested. But the idea was to attack the sea of events syndrome, right? So you deploy this thing, a lot of alerts are generated, but you want to know which alerts are interesting for you and how these things are actually related, right? So we actually do this automatically. So we can tell you something is being downloaded, we analyze it, it actually tries to exploit you, but then we see command and control connections, and all this thing, automatically we actually group them into security incidents rather than, hey, this something bad happened here, something bad happened there, right? It's also quite a bit of a research challenge to be able to do this, I think. So I think malware component, also in the previous demonstration, actually we heard that it's the #1 security problem out there right now, right? So yes, you can attack Windows 8, but the first step of the attack is you need to infect people. And then you can use that, the Microsoft vulnerability as a stepping stone, which is also important, but the first step is getting into the system, right? And malware is often being used for that. So automated analysis is a good thing. Right now, this is what everybody's investing in. But we're going to see more and more challenges in this domain as well as these systems become popular, right? The more people use it, the more evasions we're going to see because the bad guys will adapt. It always happens, and they will do this, right? It's a logical thing to do. So the types of evasions I talked about were, detecting the analysis environment, detecting the analysis system, or avoiding analysis by using all sorts of tricks. And we're seeing many classes of these attacks. So I don't think you can simply give up, right? This is a promising way to go forward, but evasion is something that I think has to be addressed. Otherwise, you'll face the problem that it's going to be snake oil, basically. You'll have all these defenses, but they will be easily bypassed. So these are things that I think we need to think about. With that, I'll pass it on to Lindsay and just show you the UI and how we deal with some of this stuff.